All right, today we are looking at applications of exponential functions, looking at why we are solving exponential functions, and you're going to see it in context. So today we're looking at applications. Our goal today, can you extend the knowledge that we talked about in the previous 3 lessons to solving exponential equations to real-world situations? And then I want you to be able to also reflect on the reasonableness of the answer. So you got to look at your answer, and that's one of the big things with this section, and in fact this course, is I want you to be looking back and saying, does this answer at least seem in the realm of possibility? So there are a couple of applications we're responsible for this year. Financial application, where we're going to be using it, is specifically this formula right here. And this is our compound interest formula. Okay, so compound interest formula. Compound interest formula. And we've talked about this in previous courses, but now we're looking at solving for unknowns. We avoided certain unknowns throughout the grade 9, 10, and 11 for specific reason. So your legend, A is your final amount or total. A, P is your principal. Okay, that's how much you invested originally. I is your interest rate per compounding period. Interest rate per compounding period. Compounding period. And I'm going to extend on that a little bit here in a second. N is your total number of compounding periods. Total number of compounding periods. And now I need to extend, or I got to add on 2 more variables that don't even appear in the equation in order to do these questions successfully. So for example, R is not in the formula, but we need to know this because this is the annual interest rate. And the other one that's not here is small t, which is time invested. Okay, so how do they link together here? Well, I, your interest rate per compounding period, is equal to your annual interest rate R, okay, as a decimal, divided by number of periods in a year. Okay, so that's your formula for I. N is equal to small t, how much time, multiplied by number of periods in a year. So all that information is very important. Now, number of periods in a year, let's talk about that. So just a small chart here. Number of periods in a year. So, make ourselves a bit of a T-chart here. Term, number associated with that. So, for example, you've probably heard the term, or I hope you've heard the term yearly, monthly, quarterly, daily, weekly. I'm just going to put the more common ones here, and bi-weekly and bi-monthly. And I guess I can also put weekly here as well. Depends on the question and what it's asking. Okay, so there are the common terms we're going to talk about. So what does that translate for us? So number of periods. Well, yearly means that there's only one period in that year because you're doing it once a year. Monthly would mean that there are 12 periods in the year that we're interested in. Quarterly, we divide the year into 4. Daily, 365 days a year. Weekly, it's 52. Put weekly twice, get rid of the bottom one here. Okay, if I go bi-weekly, I'm going every second week, so that would be 26. And if I go bi-monthly, twice a month, so that would be 24. So those are the numbers that you need to hopefully have in your head. I don't know if you want to waste cheat sheet space on that kind of stuff, but that is your number of compounding periods per year, which you're going to use here in the formula and here. Okay, so that's the financial application taken care of. Natural sciences, so you're going to see a formula look something or similar to this. AB to the x over t. All right, this one's a little bit easier, so this is your total amount, the f of x. A is the initial amount. How much did you start with? B is your growth rate. So you're going to see things like half-life, which would mean that B is equal to 1/2. You're going to see doubling time. So these are the types of expressions you'll see in the word problems. B would equal 2. There's a couple others. Those are the more common ones, but there will be others that come up. Tripling time, third life. Not very common, but your T then. Basically, how long the growth rate needs to happen. So I can explain that a little bit more. Basically, it says something will double every 2 years. So I'll just put that in brackets here as an example. Double every 2 years. So that would mean that your base is 2 because it's doubling. Your T would also be 2 for 2 years. So how about, let's make that into a 3, so it's a little bit different. Doubling every 3 years, 3, which means X is how much time has passed. All right. So there's your natural sciences. So these are the people that are going to be taking or have taken biology or planning on going into health sciences next year at the college or university level. Mathematical modeling, it's more of a pure formula, back to what we talked about. So it's just going to look straight like that. Again, this is your final amount. A is your initial amount. B is your, obviously, base. But you're looking at, in this case, an example I could give you is 10% growth. So if you had 10% growth, B would equal, at the decimal, 100% plus another 10. So your base would be 1.1. So what essentially is happening here, here's the 100%, so that's last year's population, and the 0.10 is what's being added to the population. The flip side to that is if you have 10% decay or reduction, 10% reduction each year, your base then is going to equal, you lost 10%, so you have 100%, 1.00, and we're losing 10% each year, which would mean your base is actually 0.9 in this case, 0.90. Okay? And that's what you're looking at, and I'll show you some examples coming up here. And then X is the time that has passed. most often. All right, so there we go. Those are the three types of models that we're looking at, and three types of examples I'm going to give you. So we have time to do the first example here. So Barry has decided to invest $5,000. So this is a financial question in an account that earns 8% per annum, fancy way of saying per year, and it's compounded quarterly. So answer the following. So I always like to write down the information I have. So Barry has decided to invest $5,000. So that's what he has today. So that's his initial amount. So that's his P. So he has, $5,000 to invest right today. An account that earns 8%. And I said per annum, fancy word. English people like feeling important, so they make big words. Per annum. So that's yearly interest rate. So that's our R. And I'm going to switch it to a decimal. The sooner you switch it to the decimal, the less chance there is of you forgetting to do it eventually. Compounded quarterly. So now we know how many periods are in a year. So I'm just going to go number of periods is equal to 4. So from that information now, I'll change color pens because now I can do some calculations. I know already that I is going to be 0.08 divided by 4 because it's your annual interest rate divided by compounding periods. So I haven't even got into the question yet. So you can check with your calculator, but that's going to be 0.02. And N is going to be my time multiplied by 4 compounding periods per year. I don't have that information yet, the T, because we haven't started into the question. But I have a lot of information listed there. So now I can look at A part. It should be an equation. Again, this is not an English class. Develop an equation to model Barry's investment. So we already know it's a financial one. There's only one financial formula for you to deal with, and that's it there. We know the p-value, so A will equal P is 5,000. The I have calculated, and the exponent N is going to be exactly what I've penned out for us down here. We're going to replace it with T times 4, or that's just 4T, right? We don't need the multiplication sign in there, so we can just write it as 4T. So it's the exponent 4T. And there we go. There's A part answered. Just put a box around that. B part. How much will Barry's investment be worth in 10 years? So this question tells us T is 10 years. So I can go A equals, so I'm just copying down the formula in the red box above. And yes, you can write that as 1.02. And now I know it's 10 times 4 in the exponent. There's no trouble here, no unknowns. So you can just crunch this through a calculator. So I'll get out my BAC here and turn it on. Hopefully, there we go. So 5,000 multiplied by 1.02 to the exponent 10 times 4, that's just 40. If you're not sure, if you have to do the calculation, make sure you put it in brackets for that exponent again. Calculating that, we have 11,040 and 20 cents. So let's see if my memory will hold. There we go. And a therefore statement. Therefore, Barry will have $11,040.20 after investing $5,000 for 10 years. And then the final one, final one I'm going to have to take up in the next video because I'm running out of time here. So I'll finish C part in the next video and finish up the examples. Hopefully should be able to go through the next one. So see you in a minute.